thank you very much for the invitation and for everyone to stick into the last talk. And it's great to be in person. And yes, and everyone said that. So I think it's really important for scientific interactions. So I'll be talking about something that is a bit further away from everything that was discussed here, except for the CMB, and that's the hydrogen 21 centimeter line, which is not observed yet, but it's a very young field that is rapidly evolving, and it's extremely interesting. So 21 centimeter line is created by neutral hydrogen that is between star forming regions. And we know that the early universe after CMB decoupling and to the end of the epoch of reionization was largely neutral. And the bulk of this neutral gas was hydrogen. So hydrogen produces 21 centimeter transition that is due to the interactions between spins of proton and electron. This is a forbidden transition and happens very rarely, but in the bulk of the universe, there are enough atoms to create observable signals. So we expect the signal to be produced anywhere between the CMB decoupling, basically when the universe is neutral, all the way to the end of reionization, and it's created from neutral hydrogen in between the ionized bubbles. So gray bubbles here around star forming regions are ionized. So 21 centimeter will come from all these neutral regions. And it's a very narrow line that is not too broadened by all kinds of processes. So it will, if it's produced here, it will just keep streaming and being redshifted by the expansion of the universe until it's observed today. So 21 centimeter line is expected to create tomographic scan of the universe and fill the gap between the CMB observations and the observations of the large scale structure that we heard in this talk, in this conference, and also the brightest and most distant sources that we have observed to date, such as this galaxy at redshift 11. So that's the most distant galaxy that we have seen so far, and the quasars at redshifts around 7. So that is expected to be really a trove of information about the early universe. And today we'll tell you what are the observational, what is the observational status of this field, and also how this line is created and what do we expect to learn from it about the processes at this epoch. So to give you a bit of an overview of what do we expect that happens at high redshifts, and of course we don't have observations yet to probe it, but we do have theoretical modeling and simulations that inform us. So we have CMB decoupling at redshift around 1000, and then as we see from the CMB, the fluctuations in the matter density are really small, 10 to the minus 5 relative fluctuations. And so dark matter was a bit more evolved, and so the first dark matter structures form here early on, and they managed to accrete the first gas clouds that can cool and form the first stars ever. So there is a period that is called dark ages here when there were no stars yet. So that's the period when first dark matter halos were forming. Then at some point, first stars form, and this is referred to as cosmic dawn, so the dawn of star formation. And this first star forming halos are very small, about 10 to the 5 or 10 to the 7 solar mass halos. And they form maybe 1, 2, 3 first stars. So it's really a very baby stages of the universe. And on the background, so the gas in between the star forming regions is cooling down because of the expansion of the universe, and it's neutral, so it's all neutral and cold. However, the star formation, it builds up, galaxies grow, and dark matter accretes more and more gas. And so there are bigger and bigger galaxies that are formed, and they can reionize the universe more efficiently. So at the beginning, the stars are very inefficient in ionizing the gas. But as we come to the epoch that is of more massive galaxies, they become more efficient in ionization, and they eventually reionize everything. So the gas is no longer neutral and cold, it's hot and ionized. And so from that point, we will not have 21 centimeter signal anymore. So star formation has other implications. So there are many different radiation backgrounds produced by stars. For example, Lyman alpha band photons are very important for 21 centimeter physics, as I will explain in a bit. And also stars evolve and die, and they create X-ray binaries, for example, as byproducts of their lives. So these binaries will emit X-ray radiation that can heat up the gas. So even this gas is neutral, it can be hotter, and the temperature also is non-uniform. So it's hotter around star forming regions and colder further away. So there is a lot going on. And actually 21 centimeter is sensitive to all these processes that I just mentioned. So it can tell us about a lot of things, including binary formation, which can be relevant for gravitational wave physics, even though it's very high redshift stage. Star formation and also dark matter properties, because first we are sensitive to how structure forms at these epochs, and also it's sensitive to scenarios such as dark matter annihilation if they produce photons that affect the 21 centimeter. So that I already described this. So we have a gap in observations between the CMB and the observations of large scale structure. With surveys going only all the way to redshift 3, and above that there are less and less sources seen that are just the tip of the iceberg, so we are not probing the most typical populations. And 21 centimeter signal will inform us about all these intermediate stages in the evolution of the universe. So even though there are no observations from that stage, we get hints from existing observations. So first of all, we know that reionization occurred later in times. So mounting evidence from high redshift quasars and Lyman alpha emitters and the CMB optical depth tell us that reionization was likely concluded by redshift 5. And it was a gradual, of course, transition. So this is an ionized fraction or neutral fraction of the gas. So how much gas is still neutral? And at very high redshift, so here it goes to 12. It was close to 1, so most of the universe was neutral. But then with the buildup of massive galaxies, it dropped to nearly 0, and it's close to 0 today. So of course, 21 centimeter signal will be sensitive to the shape of this curve and can tell us how reionization exactly happened. But today we have large errors, and that's one of the plots I tried to sketch in the discussion session. So there are large errors on this reionization history. On the other hand, we have some evidence that star formation started very early, in particular ALMA sees galaxies at high redshifts that are already actively forming stars, and they are actually very metal rich. So it hints to the fact that star formation started very early in these galaxies. In particular, if you take this galaxy at redshift 9.1, it started and extrapolate to where star formation should have started there, we would get to redshift above 15. And that's the brightest galaxy that we have seen in the ALMA field, which is a rather small field, so we still don't have a representative picture of what's going on. There are luminous galaxies that I just showed before at already redshift 11. It also means that they started forming stars pretty early on. And then if Edge's observation is true, then it would tell us that star formation started already above redshift 20, and first X-ray binary population formed at redshift around 16. So that means that in order to model the 21 centimeter signal, we need to take into account all these processes from early on, from the dawn of star formation that can start at high redshifts and integrate to lower times, to later times. So I already mentioned that. So 21 centimeter signal, it's called 21 centimeter because the wavelength of this transition is 21 centimeter. And then it redshifts due to cosmic expansion. So for example, from redshift 9, this wavelength will redshift to 2 meter wavelengths, right? And we need large telescopes such as radio interferometric arrays to really probe this line. There is a lot of things going on the observational side, and I'm part of most of these experiments and talking to all of them. So there are global signal experiments such as EDGES. So this is EDGES high band, which probes reionization, and the signal I just mentioned this one was detected by their low band antenna. So it looks similar, but it's sensitive to lower frequencies. And this is another team's effort, Sarah's 2 antenna, which also looks at the signals from reionization. So these 2 antennas, they only see upper limits on the signals, and there is no detection yet. And what they probe is sky average. So they have very large beam, and they just average the signal and measure it as a function of wavelength. So it's a spectral shape of the signal, which tells us the average 21 centimeter signal at every redshift. On the other hand, there are interferometers such as LOFAR, HERA, BSK that are expected to measure fluctuations in 21 centimeter signal from different redshift ranges. And this is a completely different experimental setup and different type of experiments. So if these 2 classes of experiments see the same picture, it will be very reassuring that that's what they actually real cosmic signal. This is an extremely hard observation to make because the signal is very weak compared to foregrounds. So foregrounds are 5 orders of magnitude or more stronger than the signal. The reason that we are still trying to observe it is that they have different statistical properties. So foregrounds are expected to be very smooth, while 21 centimeter signal fluctuates on small scales and on large scales, and we can build models that predict how these fluctuations look like and evolve with time, and how they relate to the global signal. So the smooth foregrounds can be removed. Of course, we need to know precisely what to do, and that's very tricky, so that's why it's a hard job. But there is hope. So that's how EDGES signal looks like in detail, and every line here that I show is actually a different experimental configuration that the team tried. So they worked for many years on this experiment, and they detected something in absorption. So I'll tell more how this is created in a few minutes, but that's a signal that they report. And again, they tried different configurations and saw the same signal again and again. So that was one of the reassuring points that that's not at least superficially experimentally dependent. And if it's true, it's a signal produced by star formation in this range when the first stars were just forming. You can map the features of the signal to star formation starting at redshift 20. And X-ray binary starting to form at redshift 16 in the large quantities and affecting the thermal history of the universe. But if you put it in the context of normal astrophysical scenarios that I will again explain more in detail in a few minutes, the EDGES deep is much deeper than expected, and everyone was shocked basically in the community when they reported this. So really it was one of the most shocking things I saw in my life. So if it's not experimental failure or systematics that they didn't account for, then it can only be explained by very extreme models in astrophysical sense, such as quasars that are 1,000 times brighter than what we see today, or some non-trivial dark matter models, for example, milli-charged dark matter that interacts with gas and cools gas down because it's still cold dark matter. So both of these scenarios are very extreme and constrained by other observations, and they're unlikely. So it's still a mystery if it's a true detection, or, well, if it's they're unlikely, but they still can happen in nature. So to date, we still don't know what's going on. Yeah.
Thank you. So when they try to explain this with the milli-charged dark matter, did they try to make also a kind of more broader study of different kind of couplings like milli-charge, dipole charge, quadrupole? I mean, or coupling to, or it was just there is this possibility, and this can explain it?
No, there was a body of work, so all the theorists jumped into that, and they tried to scrutinize,
okay, and they all,
including Julian Munoz.
Yeah, no, Julian had this, but I was wondering if other models could also be as successful, or there is something about military dark matter that made it particularly successful.
Well, military charge is just that you need something to couple to gas, and the electric charge is one of the easiest ways. It cannot be fully charged, fully electric charge 100%, because otherwise it will distort to CMB too much. So it has to be milli charged, and only a tiny fraction of it can have this charge. So 10 to the minus 6 or 3 of dark matter particles can be charged. So that's the best scenario people came up with, given all the existing constraints. I imagine that the space of dark matter models is huge, so probably there are models people haven't considered.
Okay, no, but you can say, for instance, the cross section can be velocity dependent, not velocity. I mean, you can do it like in an effective way, and then see what this particular cross section is the one that explains the signal. It corresponds to this kind of models. I wonder if this kind of more effective approach had been.
There were papers on that by Tracy Sletier and students, and that's one of the nice papers that examined this velocity dependence.
Yeah, can I also add something? It's excluded that it's a beam effect.
Sorry?
It is excluded that it's a beam effect of how it's observed in the sky. It is not a systematic issue.
Yeah, they tried to check, and they also constructed another antenna, and they constructed an antenna that bridged between high band and the low band, and that has supposedly different beam, but they claim to see this effect as well with that antenna. So to that extent, it's excluded, I would say.
I see, thanks.
Okay, so I mentioned, sorry, more questions. I mentioned earlier that the signal can be verified. So first of all, we want to see consistent global signal, but it can also give us different fluctuations from what we expect to observe. So models would predict fluctuations in 21 centimeter signal that are corresponding to this model that creates the global signal. And we looked into several such scenarios. So because the global signal is much deeper than what we expect in standard models, also the power spectrum would be boosted up, and it might be easier to detect it with SK or HERA or other interferometers. So that's why I'm saying that that would be a clear confirmation if such a power spectrum signal is found. So that's an outstanding mystery in the field. This is Saras-3 antenna that is trying to probe it, and now they placed it on the lake to avoid radio frequency reflections from the ground. So it's floating, and that they are working on the paper now. And there's interferometers that might have a chance to test this theory, this observation in power spectrum. So there are, in addition to this unverified detection, there are only upper limits. But there are upper limits from many experiments. Some of them at Cosmic Dawn, actually, this is redshift 12 to 30, and there's a bunch of experiments, LOFAR, NaNuFAR, and even MWA that probe the space, but they're still much higher than any power spectrum that we predict, even in these extreme cases. So they're still orders of magnitude above that. In the Epoch of Reionization band, so that's much lower redshifts from 12 to 5. There are also many upper limits, no detections yet. So by interferometers, so HERA is one of the best points that we have today. There are observations by LOFAR, there's green lines, and MWA as well. So we recently published the HERA paper, which is the lowest upper limit that we have at redshift 8. And it's kind of still too weak to constrain standard models where the CMB is the only background source of radiation. but it's strong enough to rule out a bunch of models of this extreme radio background signals that I will again explain in a bit. So that's again a very interesting point to be in the field. So there are very first few constraints that are made on star formation and heating. So again, to get this 21 centimeter signal at redshift 8, we need to integrate through the whole history of star formation to calculate gas temperatures. So this point can already tell us a lot about the thermal evolution and the reionization. So the future is very interesting because supposedly we will map, we will have a tomographic map of 21 centimeter signal from all this cosmic dawn, reionization, and maybe even dark ages. And with that, we can constrain thermal and ionization histories, timing of all the star formation, X-ray binary formation, and probe cosmology and dark matter physics in the new regime. And to go to really do good job there, we will need to go to space first, because ionosphere blocks very low frequencies, so we cannot probe above redshift 30 from the ground. We have a lot of radio frequency interferences that will also be avoided if we go to space and behind the moon. And that's a unique way to probe physics of dark ages before star formation, because again, it's blocked by ionosphere. So there is a lot of effort already to design and plan these experiments throughout the world. So there are some efforts in the US, the DEPR is NASA funded for prototype study, and CLE is a Netherlands Chinese mission that is already operational. They are trying to probe radio background at very low frequencies, around 10 megahertz. It's not very sensitive to do 21 centimeter, but they are doing preparatory studies and study the foregrounds in that frequency range. And then there are, again, NASA studies to roll out an array of antennas on the moon, and the Chinese mission that is planned to do a kind of a chain of satellites rotating around the moon to again probe the 21 centimeter signal. So it's a really interesting developments throughout the world on this. And so now I'll go a bit more into details of what astrophysics we expect to measure. It will be great for cosmology, but astrophysics has a much stronger impact on this line, and we need to understand it first before we can get to cosmological studies. So that's a light cone of 21 centimeter fluctuation. So time is on the x-axis and y is just a cut through a simulation that I made. And here we see fluctuations in this background. So they evolve as time evolves, and because different astrophysical processes dominate this background, this signal at different times. Yeah, that just to show you how rich it is. And also to strengthen the point that we really need to take into account all the evolution history before we can make predictions for example, for HERA at redshift 8. So all the posterior evolution, all the prior evolution is important for the current predictions. And as I mentioned already, for the dark ages here, so yellow is just very low signal and blue is very deep absorption signal. So during dark ages, we are dominated by dark matter and cosmology. And here I just assumed CDM simulation. Then we have cosmic dawn when we have small dark matter halos and first stars. X-ray background heating, X-ray binary heating dominated era, and then we get to the epoch of reionization when the most massive galaxies dominate. So fluctuations are very rich because they're first sensitive to how sources are distributed, but they are also sensitive to the spectral energy distribution of each source. So photons are not injected immediately, they have some mean free path. And distribution of this mean free passes. And so, for example, X-rays will inject energy not immediately, but further away from the source, depending on the energy. And so every star forming region imprints a bubble of heat and Lam alpha radiation and radio emission if there are radio galaxies. And that affects 21 centimeter line in a non-uniform way. So it creates fluctuations, and then if these bubbles overlap, it creates a very rich picture. And then in addition to main processes that dominate the signal, such as heating and ionization, there are also subtle effects, for example, the evolution of population in time, or very subtle effects of the Lam alpha radiative transfer that need to be taken into account to model it properly. So some specific examples. So first and fundamental effect that enables observations of 21 centimeter signals called the Southern field effect. And that's the coupling due to Lam alpha emission from stars. In the absence of Lam alpha, this effective temperature of 21 centimeter line would go into equilibrium with the CMB. And that means we would not be able to observe the gas clouds against the CMB. It would just be all in thermal equilibrium. So there would be no signal. But once the stars are emitted, produced, they emit Lam alpha radiation, which actually couples the spin temperature to the temperature of the gas. So this is a CMB temperature, and the gas was much colder. It's cooling down due to adiabatic expansion. And so stars couple the spin temperature to the gas temperature, and then we suddenly can see 21 centimeter in absorption due to star formation. So this effect is just coupling. So Lam alpha photons are absorbed. The atoms from ground state go to the first excited state. And then when Lam alpha are emitted, they can end up in one of the two of the spin flip states. And thus they redistribute this population and affect this coupling transition. So when exactly Lam alpha coupling happens, that's from simulations that we did. This peak of Lam alpha coupling can happen at a variety of redshifts depending on what astrophysics we assume. For example, if there is heavy feedback of star formation and supernovae suppress star formation, it will shift Lam alpha coupling to later epochs. So lower redshifts can be as low as redshift 15. In the most happy scenarios, it happens much earlier. For example, we get it even at redshift 30, so or even higher. So this process the coupling can occur at a variety of times, and we really need data to probe it. We cannot model it from first principles. So Lam alpha has some effective horizon. They can travel to a few tens of megaparsecs away from the sources, and they would imprint what is called Lam alpha coupled bubbles in this 21 centimeter maps. So if SK observes or does imaging, so it might be that it will see bubbles of Lam alpha coupled bubbles in the 21 centimeter maps from redshift 20, which will be very informative on how star formation proceeded at that times, what was the distribution of the source. So it's just direct image of star formation. And there are no many processes that contaminate it at that time. Another very important effect is the heating, as I have already mentioned. So in the absence of heating, gas just keeps, so that's a CMB again. And if there is no heating, gas cools down adiabatically with the expansion of the universe. But as soon as X-ray sources or other heating sources kick in, they will affect the gas temperature, and it will rise because of this energy injection, and at some point exceed the CMB. So 21 centimeter is roughly the contrast between gas temperature and the background temperature. And so it's very sensitive to all the heating that is going on. And of course, to calculate the 21 centimeter here, we need to know how the temperature evolved. So again, to integrate over these equations through the whole cosmic history. So the stronger is the heating, the weaker is the 21 centimeter signal, both in global signal, and the weaker are the fluctuations, and the harder it is to observe them. So in order to make constraints on this line with this very first experiments that I showed you, we can really only tackle very cold models that are cold during the reionization, and then they create very strong 21 centimeter signals and power spectra. So again, this process of heating is very unconstrained. First, we believe that X-ray binaries are the most dominant source of X-ray production. And so that would be related to star formation rate. But even when you relate it to star formation rate, there is quite a lot of uncertainty because we don't know how to normalize it and what was spectral energy distribution of these early mini quasars. So we get, again, a variety of redshifts at which this heating can happen. So we don't know the details. We can only model this uncertainty in our simulations and try to constrain it with data. So there is a very strong sensitivity to spectrum of the sources, as I mentioned. Low energy X-rays, for example, 0.1 keV, they will travel just a few megaparsecs away from sources, imprinting very strong bubbles around each source of heated gas that can be seen through 21 centimeter signal. But if the photons are at higher energies, for example, 3 keV photons, they will not be injected at all. Their mean free path is larger than the universe, than the size of the universe, and they just free stream. So about 1 keV photons, they get absorbed a few hundred megaparsecs away from the sources, imprinting very weak fluctuations and very diffused fluctuations in the gas temperature. So as you can imagine, Fourier transforms of these two maps would be very different. So we would get different power spectra of 21 centimeter signal. And that's indeed what you see. So these are some examples of two simulations with different spectral energy distributions of X-ray sources, but otherwise they're the same. So one assumes a realistic spectrum of X-ray binaries that's on the top here, and it's a relatively hard spectrum. And the other assumes just a power law, which is a relatively soft spectrum. So we see that for soft spectrum, there are stronger fluctuations and gas is hotter than in the harder spectrum that has overall the same output energy. And of course, you see it very differently in 21 centimeter signal. So diffused fluctuations and colder gas versus very strong fluctuations and warmer gas. So that's again just varying spectrum of the X-ray sources creates a huge difference in the 21 centimeter maps. And again, varying intensity of the sources for the same spectrum also creates a difference. For example, this solid black line here is an assumption of 1,000 times hotter X-ray binaries than what we have today. Compared to the no heating at all, this black dashed line, so we have a striking difference, and it means that experiments will be very informative in constraining this heating rates. How much time do we have? Oh, nice. I'll be faster, I think. So there are several subtle processes that were actually not included in parameter estimation algorithms and simulations, and that we considered recently. So they were known since long ago, but they were thought to be subdominant, and so no one cared basically. But we showed that in some situations that they are really important to take into account, and specifically for the models that have strong implications for the observations today. So one of such processes is Lyman alpha heating. So Lyman alpha photons that they don't only scatter and couple the spin temperature to the gas temperature, but they can also heat up the gas because of the recoils. And they can overall heat the gas, just Lyman alpha photons alone by 100 Kelvin, which is which is considerable if we don't include X-ray heating. So it's a very subtle process and complicated, but there are several contributions to it. First, there are photons emitted between Lyman alpha and Lyman beta line that are just continuum photons, and they redshift into Lyman alpha line. So these photons would generally heat up the gas, and this is a distortion they create around Lyman alpha profile. And other photons, so if there are higher atoms that are in the excited state, they can cascade to the lower states and inject photons directly into Lyman alpha line. Such process would contribute to the net cooling of the gas. So that's a distortion. This is a heating and this is cooling. So cooling overall dominates for injected photons. And so there is trade-off between heating and cooling by lambda alpha, but that's the net effect is still quite strong, can be quite strong. So if you consider a scenario where there are no X-ray binaries and only this lambda alpha coupling, it turns out that it can be very important. For example, this is a global signal. In the absence of the lambda alpha heating is this dot dashed line. But when you add lambda alpha heating, it becomes this black line. So there is 50 millikelvin difference just by lambda alpha heating alone. And that's quite significant. And in the power spectrum again, so if you ignore these photons, it's around 10 to the 3 millikelvin squared during ionization. But when you add them up, it heats up the gas. So the contrast between the CMB and gas temperature is lower. So the signal drops by 4 orders of magnitude, again, just by including the subtle physics of lambda alpha photons. And you can see how it affects gas temperature. So again, black line is including these photons. So they, the gas is heated up to 100 Kelvin. As I said, it's a gradual process, but by the end of ionization, it's quite hot. But if you ignore these photons, the universe keeps expanding and cooling down adiabatically, and that's the gas temperature that we have. It's around a few Kelvin at that epoch. So that's an example of a very minor effect that have strong implications for 21 centimeter physics. And if you consider broad scenarios, so with and without X-rays and varying astrophysical parameters, that's what you get. So black lines are without this lambda alpha heating effect, and blue are with, and this is an effect on the power spectrum. So again, these are models that are the closest for observations to reject. And then the global signal, again, there is a very striking difference between, because lambda alpha heating basically changes all these very deep absorption scenarios in which the universe is cold. Okay, so another thing to consider is what actually radio background is. And we heard from Jens that there are distortions, but they're tiny from our point of view. So the main assumption always is the CMB is the only radio background source, right? So if that's a CMB, and if we know the gas temperature, we can calculate what 21 centimeter signal is. However, there might be some other sources of radio, for example, radio galaxies, which we see today. They might exist already at high redshifts. Of course, they might be weak, but if they are a bit stronger than what we see today, they would contribute to radio background and would at this very low frequencies, and they would enhance 21 centimeter signal just by raising the contrast between the background and the gas temperature. So of course, these models were brought up into our attention because of the edges detection. People started considering them. And as I mentioned, if you boost up radio, boost up quasars by 1,000 degrees, by 1,000 factor of 1,000 in luminosity, this background is way higher than the CMB and creates very deep signals. But even if you have a mild population, it would change the CMB and create some signature. So we studied that just to see what happens. And also these stronger signals are, again, easier to rule out because their power spectrum is enhanced. So first of all, if you add the radio galaxies to the picture, they affect the structure of the lambda alpha coupled bubbles because they add radio background around the galaxy that is non-uniform and that it has some profile. And so the lambda alpha coupled bubbles will look brighter in the center. So this is an example with uniform radio background. But if you add radio galaxies that they create brighter spots and then they are more diffuse towards the edges. So again, that's something that could be probed by the SK if we image that epoch directly. And of course, it changes the power spectrum of fluctuations. And even for modest enhancements, so well, modest 300 compared to what we have today in radio galaxies, in the luminosity of these galaxies per star formation rate, there is a sizable change in the power spectrum. And so this black line shows the case of no radio galaxies, so just standard CMB background radiation, and solid orange if you add fluctuations in these radio galaxies to the picture. And the dashed line shows a similar case, but with a smooth extra radio background, so without the fluctuations. So adding extra radio background, even if it's mild, not explaining edges, but also a bit higher than what we have today, would enhance the 21 centimeter signal and would make it easier to observe this. So we need to consider the scenarios as well and constrain them with data. So now I don't have time. So I showed this slide before, and these are power spectra created by these radio galaxies. So in the extreme edge of the population that can explain edges, and we can try to rule them out with the upcoming observations. So we looked into this model with the recent HERA data, and here you see HERA data points as a function of k at redshift 7.9. And all these lines correspond to a different realization in our of the radio background and astrophysical scenario. And so there is a bunch that we predict that is higher than the HERA data points, so we can rule them out confidently. This black line shows the envelope of standard models with the CMB as the background radiation in our scenarios. And in our case, it's way below. So it's below the HERA data points everywhere, so we can barely constrain them. And that's because we do it, the SLAM alpha heating that suppresses models quite a bit. But anyway, for the radio background models, we can rule out some of the relevant scenarios. For example, this is a plot of radio background temperature versus gas temperature. And orange shows our priors for these temperatures. They're uniform in model parameters, but non-uniform in temperatures. And the blue are posteriors after HERA. So we see that this chunk is ruled out already. And then in terms of model parameters, we model the strength of radio background and the strength of X-ray heating. So they both are quite constrained. Especially you can see it well in the 2D panel here of radio versus X-ray. So this white part is consistent with data, and this is ruled out. Vice versa, this is ruled out, and this is all consistent. And other parameters, such as, for example, optical depth of the CMB, are pretty flat because in our models, the most sensitive. The most important things to constrain are the radio background and X-ray heating. This doesn't add to our understanding of edges, however, because HERA probes much lower frequency, much lower redshift range than edges, and models that peak in HERA range are actually very low in edges because it's just a different subset of models. So there's still no understanding. And finally, of course, we need to model reionization. So I put it last because it does affect 21 centimeter only at the very tail of what I showed you. So only redshifts between 10 and 6 or 5. It's a very important process, and there are many complicated astrophysical processes that contribute to reionization. And there are state-of-the-art simulations such as CODA that run on supercomputers. So I think it took a month on a Titan, also some big supercomputer in the US to run, taking the whole supercomputer for itself. But they can run only one realization of such simulation and study how reionization happens. And it's not good enough for our parameter study, of course. So we model reionization in a more simplistic way, roughly like that, not exactly, but just splitting it into ionized and neutral bubbles. And then we can constrain ionization fraction through the strength of these fluctuations. Right, so HERA, for example, is most sensitive to models that have midpoint of reionization within the band, because then the power spectrum peaks, and yeah, I'm almost done. We do consider standard models with CMB only, and with a complicated galaxy ionization model in the HERA paper. So that's work done by Andre Messinger and his group. And finally, I mentioned dark matter physics, so it can be constrained with 21 centimeter again. The constraints are weak, and also, for example, HERA and LOFAR and others, they are not adding to understanding edges in these models, because again, the models that are bright in edges are weak in the HERA and LOFAR bands. So this is one of the latest papers that came out on the constraints on the smally charged dark matter models from different experiments. And yeah, you can look it up if you're interested in more details, and I'll stop here with my summary. So I showed you that the 21 centimeter signal is in a very exciting stage of the field. There is a first unconfirmed detection, and there are many upper limits that start ruling out interesting models that, and we are looking forward to next data releases that are soon to come. Thank you very much.
Thank you very much for the great summary. So are there any questions from the audience? Local audience? Yeah, there are a bunch.
So as far as remember, there was an absorption dip around Z, around redshift equals 100 or something like that, though smaller than the dip.
Sorry,
as far as remember, there was an absorption dip around Z equals 100, no?
There is one from dark ages, yes. 50.
Yeah, exactly. So is that difficult to probe? Otherwise, I mean, it could be very much a complementary probe of this 21 centimeter models or something like that.
Indeed, we do need to go to space for that. As I mentioned in the beginning, there are ionosphere blocks, high redshift regimes from us, just because it acts as a mirror basically for long wavelengths, and they bounce back. And so you need to go to space to observe this dark ages regime. That's a regime where there are no star formation yet, and we only have dark matter and cosmology to probe.
I mean, because of this higher frequency.
It's low frequency.
Yeah.
So yes.
Yeah. Yes. Low frequency. Yes. Okay.
Yeah. Thanks.
When calculating the X-ray heating and you explained how that can in principle also push the spin temperature above the CMB temperature, is in those models or in that modeling actually just the free emission of that medium included as well, because it would locally lead to, of course, enhancement of the low frequency, so to say, level, and then the 21 centimeter effects would be against that background in some sense. Is that something that somebody estimated, or is it actually negligible? Is it, where does it lie, or is it not even done?
So free
from the ionized bubble you get free as well, and it's
I don't think it's included actually.
Is it? Okay. Mm-hmm.
Yeah, no. Not to my knowledge. So there are, yeah.
How big is it? Sorry.
I don't think it's big, but of course need to do a calculation to.
I have a question regarding the X-ray binaries that I'm biased, and I found very fascinating this first binary stars forming and reheating the universe. So we don't do this. This expectation of having them comes from theory and this indirect probe that you showed us, and is this the only way to know anything about them?
Thanks. So today. I forgot the percentage, but high percent of stars is in binaries, right? Just because they form from a cloud that fragments, and it's very rare to form one star. They actually formed in groups. And simulations of high redshift universe show the same. If you have primordial cloud and it rotates, there are magnetic fields there, so they fragment this cloud into clumps that cool down and form stars. So there are systems of stars formed. And then they do form roughly 30% of binaries. So we do expect binaries, and because first stars are relatively massive, we don't know what the IMF is, initial mass function, but in many scenarios, there is a high chance to form X-ray binaries that will emit X-rays, and that's something my postdoc is working on at the moment, actually, to see how many exactly and what's the luminosity that you expect. And one other way to probe them is so they might be bright in X-rays, so future X-rays missions such as LINX, if it's approved, can be directly sensitive to X-ray emission at redshift 10, for example. They probably will be very dim in gravitational waves, just because it's a very high redshift regime. Yeah, thank you.
We have any more questions from here? Okay, I see also nothing online. Okay, well then, thank you, Anastasia, again.
Thank you very much.